Hello, this is part 2 of a series of 3 videos on the dynamics of rigid rotating bodies. I encourage you to look at part 1 if you have not already done so. We are now going to look at what's called the parallel axis theorem and then look at the consequences of what we learnt in part 1 of this series. I said earlier that the moment of inertia of any body depends on the pivot point. And that, you might think, means that you need to calculate the moment of inertia every time you pick a new pivot point. But that is not true. Because what I'm going to assert and then try to show is that if you've got any body, if you know what the moment of inertia is about the centre of mass, and obviously you'll need to know that, the mass incidentally of this body is mass m, if you want to pivot it at any other point, which we'll call point P, such that point P is a distance x from the centre of mass, then I'm going to show you that the moment of inertia about point P is equal to the moment of inertia about the centre of mass plus m, the mass of the body, times x squared, where x is the distance between the moment of inertia and the point that you want to use as a pivot. The way I'm going to show that is to take this body here. I may not draw it precisely in the same shape as it was before, but you'll get the general idea. This is the centre of mass. This is the point P, where we want to know what the moment of inertia is, and the distance between these two is a distance x. I'm going to take a small element which is going to have mass mi, and that is going to be a distance xi prime from point P and a distance xi from the centre of mass. And now I'm going to use what's called the cosine rule, or the cosine law. If I reproduce this triangle here, where this side is xi prime, this side is xi, and this side is x, the cosine law says that this length of this side here, if this angle here is, let's call it theta, cosine law says that xi prime squared, this distance squared, is equal to this distance squared, xi squared, plus this distance squared, x squared, minus twice xi, that length, x, that length, times the cosine of the angle between those two sides. Just to repeat, xi squared, this side, is equal to xi squared plus x squared minus 2xi x times the angle between xi and x. That's known as the law of cosines. Now, the moment of inertia about point P is going to be the sum of all of these little elements, mi, times their distance from the point P, which is xi prime squared. But xi prime squared can be substituted by this term here. And that gets us that the moment of inertia about point P is sigma mi times xi squared plus sigma mi times x squared minus sigma mi times 2xi x cosine theta. Well, let's have a look and see what we got. Sigma mi xi squared, xi is this distance here. That is just the moment of inertia about the centre of mass, because we're talking about an element being a distance xi from the centre of mass. So this term is simply the moment of inertia about the centre of mass. This term, x is a constant, so now we've got simply sigma mi, which is going to be the entire mass of the block. So that becomes mx squared. So now I've got IP equals I centre of mass plus mx squared, which is exactly what I wanted. Except I've now got this rather ugly term at the end, and that's getting in the way a bit. But look, observe, we've got an mi multiplied by an xi, and it's a sigma mi xi. What is xi? Xi is the distance from the centre of mass. And if you go back in the first of the videos, you will see that I showed that where the origin is also at the point at the centre of mass, sigma mi xi equals 0. It was one of the very first things we did to show that provided the origin and the centre of mass coincide, and in this case they do because xi is a distance from the centre of mass and it's also the centre of the distance from the origin, then sigma mi xi equals 0. So this whole term becomes 0. And thus we're left with what we wanted, that the moment of inertia about any point P is equal to the moment of inertia about the centre of mass, which you'll need to know, plus the mass of the body times the distance squared between the centre of mass and the point at which you wish to pivot it. So it saves you working out the moment of inertia from first principles every time. Does it work? Well, we have of course already established that if you take a rod of mass m and length l, if you pivot it at one end, the moment of inertia is ml squared over 3. And if you take the same rod of mass m and length l and pivot it in the middle, the moment of inertia is ml squared divided by 12. Well, does that conform to this equation? Well, what we're saying is that, of course, the centre of mass is here. So if you pivoted about this point P, then IP, which is ml squared over 3, is going to be equal to the I centre of mass, which is ml squared over 12, because this is pivoted around the centre of mass, plus m times the distance between the centre of mass and the point at pivot, which is L over 2, half the length. And that's therefore L over 2 all squared. And if you calculate this, you'll find that that is indeed the case. That is true. And therefore, you've got a demonstration of the action of the parallel axis theorem. Similarly, if you take a disk, we have calculated that the moment of inertia about the centre of mass for a disk is mr squared over 2, where m is the mass of the disk and r is the radius of the disk. But suppose you want to swing or swivel the disk around a point P, which is a distance x from the centre of mass. What then would the moment of inertia about point P be? And the answer is, it's the moment of inertia about the centre of mass plus mx squared. And it's as simple as that. Now I want to consider a system which consists of lots of masses, all with their own individual velocities, but they are connected masses. If you like, you can think of them as being connected by some electromagnetic forces, gravitational forces, even springs connecting them all. The whole system has a velocity which is VCM. It's the velocity of the centre of mass, because this whole system will have a centre of mass, and that centre of mass will have a velocity. What is the kinetic energy of that body? Well, the kinetic energy will be the sum of the energies of all these individual masses. So we have to sum half mv squared for each of the masses. So it's half mi times VI squared. But we can say that VI in each case is the velocity of the centre of mass plus the velocity of the ith particle relative to the centre of mass. So in other words, I'm saying that the velocity of a particle is equal to the velocity of the centre of mass plus the velocity of that particle relative to the centre of mass. So now I've got that the kinetic energy is this term up here, which is the sum of half mi, but instead of VI squared, I'm going to take the square of that term, and that will be V centre of mass squared plus VIR squared plus 2V centre of mass VIR. And that's going to equal, we can take the half on the outside because that's a constant, a half times sigma mi times V centre of mass squared. Well, V centre of mass is of course a constant velocity, and sigma mi is simply the mass of the entire body. So now we've got half mv squared, and that is the kinetic energy of the centre of mass. Plus this term here, a half sigma mi vir squared. And I'll come to that later. Plus a half times 2 cancels out, so we've now got sigma mi v centre of mass vir. And now once again we've got a sigma mi times VIR, and that equals 0 for exactly the same reason that sigma mi xi equals 0 when the origin is at the centre of mass. So mi times vi relative to the centre of mass, when it is summed, becomes 0, because all of the mass times velocity terms about the centre of mass cancel out. And if that term is 0, you can forget about the whole thing. And so we find that the kinetic energy is equal to half mv squared, where m is the total mass of the body, and that's the kinetic energy of the centre of mass, plus this term here. But v is equal to omega r. So now I can pull this term down, and I can say that that equals a half sigma mi omega I ri, and these two terms are both squared, the omega squared and the r squared, because we're squaring v equals omega r. But remember that the rotational angular velocity is constant. It doesn't vary for the masses. So we can take this I term out, because all of them will rotate in with the same angular velocity. And that gives me a half sigma mi ri squared times omega squared. But this term is the moment of inertia. And so I've effectively shown that the kinetic energy is a half the total mass times the velocity of the centre of mass squared, which is the, if you like, translational kinetic energy. It's the kinetic energy of the forward movement of the entire system, plus a half I omega squared, and that is what's called the rotational kinetic energy. It's the energy stored in the fact that this whole body may be rotating as it goes along. So what we've established is that kinetic energy is no longer simply half mv squared, which we've always considered before. You also have to take account of the energy stored as a consequence of a body rotating. This is, for example, the energy that would be stored in a flywheel. We're not covering flywheels, but flywheels store energy and can use energy simply because a wheel is spinning. Let's then consider a disc or wheel rolling along the ground. Here is the disc, and it has a velocity, because it's moving in this direction across the ground, at velocity v. But it also has an angular velocity as it moves along of omega. Consequently, that wheel will have two lots of kinetic energy. The kinetic energy of the mass of the wheel times its velocity squared, or half mv squared. That's its translational energy. But it will also have an energy of half I omega squared associated with its rotation. So let's think about that wheel rolling along the ground. Here is the wheel. It is mass m and radius r, and it is travelling at velocity v, and I'm going to let it do one complete circle. So when this point on the ground goes all the way around and comes back on the ground again, the wheel will then be over here. So this point has gone all the way around and come back, but the wheel of course has been moving in the meantime. And it will have travelled a distance which of course is going to be equal to the circumference of the wheel. So that distance d is simply going to be 2 pi capital R, where r is the radius of the wheel. And we'll say that it travels this distance in a time t. So the velocity, which is this velocity in this direction, is going to be the distance travelled, 2 pi r, divided by the time it takes to travel that distance. But that time represents one cycle of the wheel. And you may remember that 1 over t is equal to the frequency. If t is the period, that is the time for one cycle to go round, the frequency is the number of cycles per second. So if 1 over t is f, then the velocity is also 2 pi r times f. But 2 pi f is omega. And so this becomes omega r. And you get the velocity is omega r. Well, we showed that earlier on, so there's nothing new in that. But now we say that the kinetic energy of that entire system is going to be half mv squared, which is the mass of the wheel times its velocity, plus the new term that we just developed, half I omega squared. That's the rotational kinetic energy. And for a wheel, which we can think of as a disc, that will be a half mv squared plus a half. Now the moment of inertia for a disc is mr squared over 2, we showed that just a little while ago, times omega squared. But since v equals omega r squared omega squared is simply v squared. So this now becomes a half mv squared plus a half m over 2 v squared. And that's a half mv squared plus a quarter mv squared. And that's 3/4 mv squared. So notice now that the kinetic energy of a wheel that is rolling along the ground is no longer simply half mv squared, because you also have to add the rotational kinetic energy, and you get a total kinetic energy, in this case, of 3/4 mv squared. Consider that wheel rolling down a hill. It starts up here and it eventually gets down here. It's stationary here, we let it go, it rolls down the hill, and by the time it gets to here, it's travelling at speed v. Now, classical mechanics tells us quite simply that the potential energy when it was stationary here will be converted into kinetic energy when we get here. And in the good old days, we would simply have said that the potential energy which is mgh, assuming that the wheel is a distance h above the ground and has a mass m. mgh is the potential energy, and then when it gets here it would have kinetic energy of a half mv squared, we would say, and that will enable us to calculate that v squared is 2gh. And that would be wrong, because we've forgotten that there is also rotational kinetic energy here. And so now we have to say that mgh is equal to the kinetic energy of translation plus the kinetic energy of rotation. And we showed that that was 3/4 mv squared. So that equals not half mv squared, but in this case 3/4 mv squared, and that means that v squared is 4/3 gh, not 2gh. You'll recall that we said that the torque, tau, is equal to the moment of inertia times the angular acceleration, but the torque is also the force applied times the distance from the point at which the force is applied and the pivot point, provided the force is applied perpendicular to the rod. So if we take a rod and we put a pivot point in the middle, and then we have a force upwards on that side and downwards at that side, so they're both contributing to spinning this rod around the pivot point in a circular direction, and let the length of the rod be L, then we know that the total torque will be twice. This is a force here, and this is the same force magnitude here. We know that the total torque is going to be twice the force times the distance, because you've got force times distance this side and force times distance this side, and each of them is going to be L/2 away. So this is going to be twice times the force times the distance, which is L/2. The angular acceleration, alpha, from this formula here, is tau divided by I, which is going to be 2 times F times L/2 divided by I. Well, we showed that for a rod, where the pivot point is at the centre, the moment of inertia is ml squared divided by 12. And you can simplify that if you wish, but that's a way of identifying what the angular acceleration will be if you have a rod which has got forces acting on it in this way. Now I want to consider a pulley system. Here's a pulley with a rope going over it, and at the end of the rope we've got a mass M. The pulley is essentially, of course, a disc. Normally we talk about a pulley being massless, but on this particular occasion the pulley is going to have a mass M. And let's have a look, and it's got a radius R. So let's just have a look first at the forces that are applying here. There will be a force, the gravitational force of mg acting down. There'll be a tension in the rope, and the tension in the rope acts both ways, otherwise the rope's clearly going to break. The torque on the system is going to be the force times the distance, which is the tension in the rope times the radius. There will also be, of course, this pulley will have to be suspended from the ceiling, and there will be a tension T2, but that contributes nothing to the torque because it goes through the pivot point. And remember, we said any force that goes through a pivot point has no effect because the distance from the force to the pivot point is 0, so it has no effect. So tau is T times R, but as we've already shown before, tau is also equal to I times alpha. So that equals I times alpha. And for a disk, we've shown that the moment of inertia I is mr squared over 2. times alpha. So TR equals mr squared alpha over 2, which means that T is equal to mr alpha over 2. But as we showed in the previous video, alpha times r is simply the acceleration, and that gives us that T equals to ma over 2. Just a reminder that all the capital M's are the mass of the disk, all the little m's are the mass on the block here. And so you've got that the acceleration, the force downwards is mg, minus the force upwards, which is T, which is ma over 2, will be the force, the net force acting downwards, and that's going to be ma. And that means that the acceleration that this little mass will have going down is going to be mg divided by little m plus capital M over 2. So in other words, it's not going to fall with the speed of gravity. It would if the pulley were massless, because if you put, this is capital M, if you put capital M equals 0 in this equation, you simply get the acceleration is mg over m, which is g. But if you have a pulley, the reason that the acceleration will not be equal to g is because some of the force that is acting downwards is actually being translated into rotational energy in the pulley, and that will therefore reduce the amount of force that is acting downwards on this mass, and that reduces the acceleration with which it will fall to the ground. Next, I want to consider the playground seesaw. This is a essentially long rod which is usually balanced or usually pivoting in the center. And what we're going to say is what happens if the net torque is 0. So what we're saying is force times distance of all the objects on it is 0. And also we're going to say that the sum of all the forces is 0. Well, this means that if we put 4 people on the seesaw, and we'll say this one is mass m1, this is mass m2, this is mass m3, this is mass m4, that's m3. Then the forces acting downwards, of course, are going to be in each case m1g, m2g, m3g, and m4g. And what we're going to have to do is to multiply. This is going to be distance x1, this is distance x2, this is distance x3, and this is distance x4. So consequently, if the torque is 0, we can say that m1g times x1 plus m2g times x2, which is these two forces, force times distance, is balanced by the other side, m3g times x3 plus m4g times x4. m3g is the force times the distance, m4g is the force times the distance. And that's the formula that dictates where these people have to stand depending on their weight. Typically you'll be given certain masses, maybe you'll be told where 3 of them are standing, and you'll be asked where does the fourth have to stand in order for the seesaw to balance, and you'll need that formula to do that. If all the forces are equal to 0, because of course the seesaw itself doesn't move, then what you can say is that the total forces, m1g plus m2g plus m3g plus m4g, must be exactly balanced by the normal force that's acting upwards on the pivot. And that normal force will be m1g plus m2g plus mg3 plus m4g. So that the resultant force is 0. The force acting upwards, which is the sum of all these forces, is equal to the sum of the forces acting downwards. I want to consider a hinged rod, and it's hinged to a wall. So there's a hinge at this point here, and this rod can, as it were, rotate around that point. The rod is length L, and it's got a mass M. And the question is, what force do I have to apply here to stop the rod from falling down? You will recall from the first video that we did in this series that the centre of mass is the point at which all the mass can be considered to be acting. Now you'll remember from the first video in this series that we described the centre of mass, and we said that the centre of mass is the point at which all the mass of an object can be thought to act. So if we take this long rod here of mass m, we can say that it can be thought of as acting at the centre of mass, which is obviously going to be, if it's a uniform rod, at the centre of this. And we can say that there's a force which is the mass of the rod times g, which is the gravitational attraction, and the torque, therefore, is going to be mg, the force, times the distance, and the distance is the distance from the pivot, which is L/2. So that is the torque acting in this direction. What about the torque acting in that direction? That's the force I am using to push the rod up. Well, that torque is going to be the force that I use times the distance from the pivot, which is L, the length of the rod. And if there is going to be no movement, if this rod is not going to move, then the two torques must balance, which means that FL must equal mg times L/2, and if you reduce that, you get that F is equal to mg, sorry, that should be a capital M, capital mg/2. And that might lead you to a puzzle. After all, the total mass, or indeed the total force of the rod acting downwards is mg. How can I hold it up with only mg/2? There seems to be a disparity. But of course there can't be. The total force acting in both directions must be 0. Well, there's a force acting downwards of mg, and there's a force acting upwards, that's acting downwards, and there's force acting upwards of mg/2, that's my force acting up. So where's the difference? And the answer, of course, is that there's another force acting upwards on the pivot. The pivot itself is helping to support this rod, and the other mg/2 is actually at the pivot point. That force of mg/2, make it clearer, mg/2, that force at the pivot point, of course, contributes nothing towards the torque, because any force acting through the pivot point has a 0 torque, because the torque is force times distance, and the distance is 0. Now let's take exactly the same rod, pivoted in exactly the same way against the wall, so it is free to swivel, and it will have, as we've said before, the mass times g is the force acting down from the centre of mass. But instead of me holding it up, as I did on this occasion, this time we're going to have a wire at an angle theta, and that wire is attached to the wall. That wire will have a tension, and what we want to know is, what is the tension? Well, we can resolve the tension into two parts. It will have a component T sine theta acting upwards, and a component T cosine theta pulling this way. But that is having no effect at all, because it's just pulling the rod into the pivot, and that will achieve nothing. And so now we can equate the two torques. In the downwards direction, we've got, as we had before, mg times L/2. The force times the distance. The distance, the length of the rod is L, so the distance here is L/2. Going in the other way, you've got T sine theta times the distance, which is L. And if you reduce that to its basic form, you find that T is equal to the mass of the rod times G divided by 2 sine theta. And what you can see there is that as theta goes down, T goes up. So as you reduce this angle, the tension in the wire will increase. If you increase the angle, then the tension will reduce. Now I want to consider a ladder leaning against a wall and ask, what is the safe angle for that ladder to be placed at? So here's the wall, here's the ladder, and it's at an angle theta. And you'll understand that the narrower that angle, the more likely the ladder is to slip. So we want a minimum angle that that ladder has to be in order for it to be safe. What are the forces that are acting in this diagram? Well, there will be a force acting out from the wall as a consequence of the ladder pushing into the wall. There will be a normal force acting upwards as a consequence of the ladder's force on the ground. There will be the gravitational force of the ladder, which can be thought to operate through its centre of mass. So the entire mass of the ladder, which has a mass of m, is acting down here, that's mg. There will be a frictional force acting in this direction, opposing the tendency of the ladder to slip in that direction. And we're going to say that the coefficient of friction between the ladder and the ground is μs. Now we want stability, and stability means we don't want this ladder to move. So if there's no movement, there must be no net force. So that means that the sum of the forces in the horizontal direction must be 0, and the sum of the forces in the vertical direction must be 0. Well, what have we got as forces in the horizontal direction? We've got WF moving in that direction and the frictional force acting in that direction. And if there's to be no movement, those two must be equal. So we've got that W is equal to FF, the frictional force. What about the vertical direction? We've got mg in this direction and we've got a normal force in this direction. And if there's to be no movement, the two must be equal. So N must equal mg. Now we look at the torques. And for a torque, we need to think about a pivot point. You can choose any pivot point you like. But if you've got any brain, you'll choose a pivot point that gets rid of some of the forces, because remember, a force that acts through the pivot point contributes nothing in terms of the torque, because it is a distance 0 from the pivot point. And I've got two forces acting through this point here. I've got the normal force and I've got the frictional force. So I'm going to choose this point here, point P, is going to be my pivot point, which means I've only now got two other forces to think about. One of them is acting to pull the ladder in this direction, one of them is acting to push the ladder in that direction. So if we've got stability, those two torques must balance. Well, first of all, I've got the force mg, but I need to know what the component is that's acting perpendicular to the ladder. And that is going to be mg times the cosine of this angle theta. So the force is mg times the cosine of the angle theta, mg times the cosine of the angle theta, times the distance from the pivot. And if the whole ladder is length L, then the centre of mass is a distance L over 2 away from the pivot. So the torque is going to be the force times the distance. And that's going to equal this force, which is the normal force against the wall. But again, I need to know what the perpendicular force is against the ladder. And that's going to be W sine theta. That's the force, the perpendicular element of the force, times the distance, which of course is now the entire length of the ladder times L. Just to point out that, of course, there will be another component of mg acting in the direction of the ladder, and there'll be a component of W acting in the direction of the ladder. That has no effect whatsoever. It's only the perpendicular forces that have any effect. And if you reduce this formula here, you will get that W is equal to mg over 2 times the cotangent of the angle theta. Just to remind you what that means, the tangent of an angle is the sine divided by the cosine. The cotangent of an angle is the cosine divided by the sine. So that's the cotangent of the angle. But let's remember that W is the frictional force. And the frictional force is always, as we showed in the video I did on friction, the coefficient of friction times the normal force. So for W we can have mu s, which is the static coefficient of friction. Mu s times n is W, and that equals mg over 2 cotangent of theta. Cotangent of theta. But n is mg. And now you'll see that the mg's themselves cancel out on both sides, and what you get is that the cotangent of theta is equal to twice the coefficient of friction. What that means is if that angle is smaller than 2 times the coefficient of friction, if that angle is smaller than twice the coefficient of friction, the ladder will slip. But provided that angle is greater than twice the coefficient of friction, it's stable. I now want to think about three-dimensional objects that are rotating. And here you'll see that we've got a problem. When we had a two-dimensional object, all we had to do was to stick a pin through it, and we called that the pivot point. When you've got a three-dimensional object, you need not just a pivot point, but an axis. And if you take a potato and stick a skewer through a potato, you can see that you can push the skewer through at a particular point, but it can then take many directions. So when we've got a three-dimensional object like a potato, and we want to spin it around a pivot point, we don't just know that there's a point, we need to understand what the axis of rotation is. For 2 dimensions, we said that the torque was equal to the force times the distance of the force from the pivot point. When it comes to 3-dimensional objects, we now have to use vectors, and we say that the torque vector is equal to r cross f, where r and f are vectors. R is the vector distance from the application of the force to the axis, and F is the force itself. And this is what's called a cross product. It's a particular way of multiplying vectors. I may make a video on vector manipulation, including cross products, but pending that, let me just briefly explain what a cross product is. If you have a vector C, and you say that that vector C is equal to the cross product of A times B, what that means is that the magnitude of C, the magnitude of the vector C, will be the magnitude of the vector A times the magnitude of the vector B times the cosine of the angle between A and B. So if you have A and B with an angle between them, then if you've got a cross product, the magnitude of C will be the magnitude of A times the magnitude of B times the cosine between them. And so if you simply take this as a cross product term according to this principle here, you get that the magnitude of the torque is equal to R times F times the cosine of the angle between them. And that was precisely what we said when we said that you have to take the force times the cosine of the angle if it isn't perpendicular to the rod times R, which in this case would be the distance between the force and the pivot point. But here's the other point about a cross product, C equals A cross B, and that is that the vector C is perpendicular to the plane of the vectors A and B. The plane of the vectors A and B is the paper, And so the vector product C actually is perpendicular to the paper. It either comes out of the paper or it goes into the paper. How do we know which one it is? Well, you always take the first and the second and you ask yourself, which way do I have to rotate A in order to get to B? If I have to rotate A clockwise, which in this case I do, then you use the corkscrew rule. If you go clockwise, then the corkscrew will go into the paper. So in this case, A cross B would result in a vector C perpendicular to the plane of the paper going into the paper. If on the other hand it was B cross A, then for B cross A, B has to go anti-clockwise to A. So B cross A would mean the corkscrew would go anti-clockwise, which means it would come out of the paper. And so if we have tau, the torque, as a cross product of force times distance, or R cross F, then what we're saying is that tau will be perpendicular to the plane of the force and the distance. In other words, tau will tell us where the axis is, because tau acts along the axis. Let me just illustrate why that is in case you're wondering. Here is a cross section of the potato. I've cut it in half. This is the skewer going through the potato. Here is my force attempting to make that potato swivel on the skewer. Here is the distance between the force and the pivot point, the skewer. And so tau will be at right angles to the plane of these two vectors, which means it will be along the axis. In other words, it will be along the line of the skewer, the axis of rotation. Now if tau equals, or the torque is equal to R cross F, force times distance, but as a cross product, then I will also show you that the angular momentum for three-dimensional objects is equal to R cross P, where P is the ordinary momentum. And I'll also show you that angular momentum will be a vector along the axis, or along the corkscrew that's gone through, along the skewer that's gone through the potato. We know, because we showed it before, that the torque is the rate of change of angular momentum. So if we do that in terms of vectors, we have that the vector torque is equal to the rate of change of the vector angular momentum with respect to t. If I now substitute that L for L equals R cross P and use normal vector manipulation, what I will get is that the vector tau is equal to dr by dt times P, where these two are both vectors, plus R times dP by dt, where these are both vectors. This is just manipulation. Where it's R cross B, it becomes dr by dt times P plus dP by dt times R. That's the way you work out what tau is if tau is dl by dt and L is R cross P. Well, what is dr by dt? That's distance divided by time, that's velocity. So now we get V, isn't it, these should be cross terms here, V cross P plus R cross, what's dP by dt? What is the rate of change of momentum? Force. So you get a velocity vector times times the momentum vector plus R times F. But this is going to be 0. Why? Because momentum is mass times velocity. And so you've got essentially a velocity cross velocity product. But remember what I said? That where you've got a cross product, the magnitude of that product is equal to the magnitude of the two terms multiplied by the cosine of the angle between them. What is the angle between the velocity and the velocity? 0. So if the velocity and the velocity are in the same direction, and the velocity and the momentum are in the same direction, the angle between them is 0. The cosine of the angle therefore is 0, and therefore the whole term becomes 0. So V cross P is 0. And that gets you that tau equals r cross f. And we derived that by starting from this term here. So let's just review what that means. Here is the potato, cut in half, and we're looking at it edgeways. The skewer is coming through the potato like this. That's the axis of rotation. Here is my force, here is my radius. And so the torque will be force times radius, and the torque will be in the direction of the skewer, and so will the angular momentum be in the direction of the skewer. And remember the corkscrew rule: if the force acting would cause the object to turn clockwise, then the angular momentum and the torque are both acting into the paper. If the force were to act in such a way as to cause the potato to rotate anti-clockwise, the torque and the angular momentum would come out of the paper along the line of the axis. Now those principles are going to be key in the final video of this series, where we're going to be looking at the very peculiar behaviour of gyroscopes.